Alrighty, let us wrap up rotation so we can move on to other things. So today we are wrapping up angular momentum. I defined it last time, and we're going to go and do some problems. For angular momentum, you will do some problems where you'll be expected to get some numbers. But I really will be focusing more conceptually on angular momentum and looking at angular momentum conservation for simplified problems, which are ones that I will do today. Angular momentum, admittedly, is quite complex to wrap your mind around because you're dealing with 3D vectors, there's the right-hand rule. But if you do take the time to figure it out, the physics majors might be worth really thinking about this and trying to really imagine what these vectors look like. You can explain a lot of really cool things with very little effort if you argue them using angular momentum. So just to remind ourselves, angular momentum we define as the cross product of the moment arm and the linear momentum of the system. So going back down, if I have some particle that is moving with some momentum p about some axis of rotation or some pivot point that I choose to measure from, which I'm going to place my origin at. Where you measure angular momentum, torque, all of that depends on having some axis of rotation, some sort of pivot point, which again, usually in the problem is very obvious what to choose, but you are free to choose whatever you want in terms of the axis of rotation and doing the analysis from that axis of rotation. In this case, let us use the origin. So in this case, I would say, again, by the right-hand rule, my fingers point along the direction towards R, and then my fingers curl down so that they then point towards P. If I do that, my thumb points into the screen. So I would say that L is into the screen in this case. L, recall, is always perpendicular, right? Any cross product. Torque, the torque vector is perpendicular to the moment arm and the force. Angular momentum, the vector is perpendicular to the moment arm and the momentum. We can define the total momentum of the system similarly by adding up all the individual momentums of the particles. In cases where all the particles are arranged in some sort of extended object, a solid sphere, a disk, a cylinder, or a pulley, where we have, pre-calculated rotational inertias, for example, we can write down the total angular momentum of the system as just I times omega, which matches the analogy we had before where the momentum was m times v. Here, angular momentum is I times omega for extended objects, with the caveat that their rotation axis is not changing. If the rotation axis is changing, you have to be more careful because the rotational inertia is changing in that case. So you can't just write down L equals I omega. You have to treat both the inertia and omega as a function of time. Anyway. And then similar to momentum, we looked at how is the total momentum of the system changing. For regular momentum, it was the net external force that changed the momentum of the entire system. For angular momentum, it is the net external torque that changes the angular momentum of the system. And just like what we did for linear momentum, if that net external torque is 0, then that says that angular momentum of the system is conserved. Similar to what we saw with linear momentum. And I'll just point out, like linear momentum, this can often be applied if you do it immediately before and immediately after a collision. And we'll look at this as there are some cases where the net external torque is always 0, and then I could look at the angular momentum at 2 points really separated in time. In this case, like regular momentum, if it's right before and right after a collision, you can still apply angular momentum conservation. Because any external torques do not have an appreciable amount of time during a very short collision to really change the momentum of the system. Alrighty. So what I wanted to do is just do some examples today. Not all of them have to do with angular momentum. There's a couple from torque that I think are worth reviewing. Let's try the yo-yo. You have a yo-yo where there's a cord that is wrapped around some sort of ball bearing, some little pulley in the center of the yo-yo. Then the yo-yo itself has some larger extent R. And if I arrange the yo-yo such that the cord wraps up, from underneath the ball bearing like drawn, the question is, what happens if I give a very slight tug on the rope of the yo-yo? All right, so you tug on the rope with a force T. Explain the motion of what's going on. Now in this case, it depends. One example I might say that if the table is frictionless, then there is only one force that is torquing the system. If I blow up the yo-yo so it's quite large, you have the pulley in the center. The yo-yo wants to rotate about this axis of rotation. It wants to rotate about the center of the yo-yo. But then that means that there is some distance down here to where the force is in contact with the yo-yo. There is some small moment arm as a result. In that case, I could define a torque that is on the yo-yo as R cross F, which it looks like the moment arm and the torque are 90 degrees from one another, so I would say that this is just RF, or I guess RT in this case. And then whether it's positive or negative, again, you have to think about whether this wants to make the yo-yo rotate counterclockwise or clockwise. In this case, if I look at this, I can convince myself that if there was nothing else in the system, I'm essentially pulling the bottom of the yo-yo towards me. And if it's restrained to fix around that rotation axis, that is counterclockwise rotation. And we say that clocks are negative, so counterclockwise is positive, clockwise is negative. So then that, by Newton's second law, results in an angular acceleration. Right, so I guess it's positive. We would also say that torque points out of the page in this case, if we wanted to specify the vector. That also implies that the angular acceleration points out of the page. And so after some time delta t, omega eventually points out of the page. So omega is going to want to point out of the screen. So by the right-hand rule, my fingers can then curl around my thumb. And that shows that the yo-yo wants to rotate counterclockwise. So then that would be counterclockwise rotation, or the yo-yo unspools. Not upspools. In this case, I would pull my rope out, and the yo-yo would essentially just unwind, and the rope would get longer and longer and longer. Chances are the yo-yo would also travel with me, because there's no other forces acting on the yo-yo, so there's going to be a linear acceleration towards the right. But as it does that, the yo-yo will also unspool. So the distance between me and the yo-yo might get longer as I pull it. Now what if there's friction? If there's friction, then there's a point of contact right here where the yo-yo is going to be resisted. It's going to want, if I'm pulling the yo-yo, I'm trying to make the yo-yo move to the right. Friction opposes motion. It wants to keep things stationary for static friction. There's going to be a friction force that points back towards the left as a result. The axis of rotation is in the same place, though the moment arm in this case is much larger for the friction force. There's still that little bit of torque from my pull. And you can imagine if it's large enough, it could still dominate, but let's assume it's not anything, too crazy. So in this case, it looks like the torque on the yo-yo is not RT, but it looks like big R than the force from static friction as I pull. And I put a minus sign because if I do the cross product, down R, fingers curl towards F, my thumb points into the screen. Which implies that the angular acceleration also points into the screen. Which implies that given enough time, omega will eventually point into the screen. Which in this case is clockwise rotation. Because again, if my thumb points into the screen, I curl my right hand fingers around. The only way I can do that without snapping my wrist is if my fingers curl in the clockwise direction. So the yo-yo is going to want to then spin or roll in the clockwise direction. Or in this case, it wants to roll to the right. So in this case, the yo-yo spins up the rope. It spins in the opposite direction, so not only am I pulling it to the right so that the entire yo-yo is moving to the right, but the yo-yo itself is rolling up the rope as you do it. I made a video of this in grad school, so that's why you can see the resolution of this is terrible. So this is the same setup. I have a table, which is clearly not frictionless. I have a yo-yo, and the cord is wrapped underneath the yo-yo ball bearing like this. I'm going to pull ever so slightly on the string. Not enough to get the yo-yo really to start moving, but because of the torque, it will appear like it flies forward and wraps itself up. Let's do it again. Right, I pull my hand ever so slightly, right? My hand only goes a tiny bit, yet the yo-yo itself traverses the entire string fairly quickly. Friction in this case actually is what is causing the yo-yo to move that fast. In this case, friction is what is causing the yo-yo to speed up, because friction is torquing the yo-yo to wrap itself around the string. All right, that's a fun little demo that I like. Let us do now angular momentum conservation. So let's suppose I am holding a giant bicycle wheel that I'm holding horizontally. And the bicycle wheel itself is spinning. So you can imagine just a big wheel with two spokes. I'm holding onto the spokes, and then the wheel itself is rotating. And let's assume that the rotation is such that the angular velocity of the wheel points straight up. I could look at this and define my system as me plus the wheel. In which case, I would say that angular momentum is conserved. Why? Because there is no net external torques. There's gravity pulling down on both me and the wheel. Let me just do the example of the wheel. There's a gravitational force that's pulling down on the wheel. But it is along the axis of rotation. Omega points along the axis of rotation. Gravity points along the same axis. So in this case, the moment arm for gravity equals 0. There's no torque as a result of gravity. And then similarly for me. Similarly also, the force from the ground pushing up on my feet also points along my body. So I am not getting any net torque as a result. I do not start rotating as a result of the floor. So in this case, I could ask, what happens if I then rotate the wheel such that I make it so that the angular velocity of the wheel is pointing in the opposite direction? So essentially I take the wheel and I flip it over. Before it was spinning this way, but then as I flip it over, it then is spinning in the opposite direction. So the angular velocity now is pointing the other way. That has changed the angular momentum of the system. I have taken the angular momentum, which originally was pointing upward. Angular momentum always points in the same direction as the angular velocity. I have then switched it over, so the angular momentum now is pointing downward, which doesn't sound like it's conserved in that case. And what's happened in this case is that it's not conserved when I did that. When I rotated the thing inside the system, I was torquing the wheel. I was causing the wheel to rotate. In this case, I caused it to rotate by flipping around. By torquing the wheel also torqued me. So we essentially exchanged angular momentum with each other. But then my feet in contact, my body wanted to start rotating. Because I torqued the system, so angular momentum was exchanged. Like linear momentum. But since my feet are touching the floor, the friction-filled floor, the feet, you might say, well, you did not start rotating. And that's because essentially all the angular momentum got drained away by the friction on the floor. By rotating the wheel, I torqued the wheel torqued me, my body wanted to start rotating as a result. But then friction from the floor also, essentially balanced it out and prevented me from not rotating, or prevented me from rotating. Now let's take the same scenario. But I'm standing on a frictionless spinning disc, or a disc that is allowed to spin, and it's frictionless. If I define that as my system, again, angular momentum is conserved. So originally, angular momentum, was pointing upward along with the wheel. I then switch the system to be such that the angular momentum vector, or the angular velocity vector of the wheel, now points downward. But I'm on a disc that is free to spin, so there's no torque from friction between me and the ground. And so in this case, the angular momentum still wants to remain exactly what it was before. So that suggests, as a result, there must be some new angular velocity that I gain as a result, such that when I add up the angular momentum of my body in the angular momentum of the spinning wheel, they add up to the original angular momentum, before I started this entire endeavor. Again, this is a conservation principle. Conveniently, I have a demo of this. So here's the idea. Again, John Brockman and I demonstrating this. Here's me. I have a big wheel, and John is going to help me spin up the wheel. So there's going to get some angular velocity going in the wheel. I'm then going to stand on this disc, which is frictionless, and will allow me to, if I have any angular momentum, will allow me to move. So I'm going to comfortably stand up, and then I'm just going to rotate the wheel. All I did was rotate the wheel. I'm going to rotate the wheel a little more, and then I stopped. I brought it back to what it was before. Then I rotate the wheel in the other direction. In this case, I'm changing the angular velocity vector of the wheel. As a result, I'm trying to change the angular momentum of the system, but because angular momentum is conserved, by me changing the angular momentum of the wheel, my own angular momentum changes to compensate, such that the total angular momentum of me plus the wheel always remains exactly the same. And you can see the more dramatically I bend the wheel, the faster I move as a result. Because my body is compensating to keep the total angular momentum of this entire thing exactly the same without changing it. Because there are no net external torques acting on us. Yeah. Fun one to do in person, unfortunately for us, but glad we were able to figure out how to record it. And again, that's just the idea of angular momentum conservation. The total amount of spin in the system is retained as long as there are no external torques acting on the system. You might have heard the statement, like back when you were learning how to ride a bike or something like that, that you just have to get moving. It's harder to fall down when you're moving. There's physics behind that. There is a physics argument of why that's true. And it's angular momentum conservation. So let's look, let us imagine, where's my hoop? Let's imagine this hoop, but we're going to look at it from a side view. And we're going to consider the case where I have the wheel not rotating and I just kind of let go. And then we're going to do the case where I first give the wheel a push so that it's rotating a little bit. And then we're going to study the motion of that. And I have another video. So we have a stationary wheel. So here's the ground, and here's the wheel. Again, we're kind of looking at it from the side. So the wheel is kind of going in and out of the page, by the way I've drawn it. And I have it slightly at an angle. Since it's stationary, it initially has no angular velocity. It initially has no angular momentum. It's not rotating in any way. But there is a torque on the system. If I redraw the wheel. There's a torque acting on the system, which is due to gravity. Gravity is pulling down the wheel, from the center of the wheel. and is torquing the wheel because the axis of rotation in this case is right here at the ground. The wheel itself is not spinning, so using the center of the wheel as the axis of rotation doesn't really make sense in this case. But the entire wheel itself is kind of tilted to the side. Our intuition says it's probably going to fall over. We can argue why that is the case by saying, okay, then if the axis of rotation is rotating about the bottom of the wheel as it just plops, its axis of rotation is where it's in contact with the ground. So then there is a moment arm that goes from the axis of rotation, I didn't want green, that goes from the axis of rotation out to the point where gravity is acting. You have R, and you have F sub G. If I do the cross product, right hand fingers along R, sweep them down so that they point downward towards where gravity is. My thumb points out of the screen. So I would say that the torque vector, whatever it is, points out of the screen. As a result, by Newton's second law, the angular acceleration eventually points out of the screen. So given enough time, the angular velocity will eventually point out of the screen. So in the plane of the screen, page, whatever, the wheel ends up rotating, and it rotates. Again, if my thumb is pointing out of the screen and my right hand fingers curl around my thumb, that looks like it rotates counterclockwise. I cannot spell today. Or it plops over to the left and just rotates counterclockwise until the entire wheel hits the ground. The wheel falls over. Now let's consider the wheel that is already rotating. I give it a push forward. There's already some spin associated with the wheel. I'll draw it essentially, more or less vertically in this case. Well, it has to be slightly off. Slightly tilted. Though you could tilt it even more. But just to make my vectors a little clearer. So it's rotating into the page, and you can think of it, if I was staring at the page, it would be getting farther away from me. That requires the rotation to look something like this. So that if I curl my right hand fingers in that same direction, my thumb points to the left on the page. So that is the initial angular velocity. So the initial angular velocity is non-zero and points, I'll just say left, given how I've drawn this. And so therefore the angular momentum also points left on the screen, on the page. However, again, there is a torque on the system. If the wheel is slightly bent or at an angle, there is a torque that is pulling down as a result of gravity. That torque on the system, you can think of, it is trying to make the system rotate about this axis of rotation. The torque is trying to make the entire thing rotate counterclockwise again. There is again a torque that points, in this case, it points out of the screen, just like what we said before. Torque points out of the screen. I was going to write out. So as a result, there is an angular acceleration that points out of the screen. So now if we think of this in terms of angular momentum, as a result, since there is an external torque, L will want to turn to also point out of the screen. Or you can, if you want, you can think of this in terms of omega. Just how we saw if there's an acceleration this way and my velocity is this way, given enough time, the velocity is going to move itself to point in the same direction. In this case, I have an angular acceleration this way, perhaps a angular velocity this way. Eventually, the angular velocity is going to want to turn towards this direction. What's different is because it's angular velocity, that means if the angular velocity is pointing up and it's going to rotate like this, originally the object was doing this, but then as it rotates, it starts to then rotate in a slightly different direction, again by the right-hand rule. My fingers are curling, it starts, when the angular velocity is this way, it starts rotating kind of in and out of the screen, but then as the angular velocity turns, and the motion is always perpendicular to that vector. Maybe I'll just grab a vector. All right, if this is my angular velocity, then the system itself is rotating, again by the right-hand rule, it's rotating something like this. But then as the angular velocity rotates, the entire system starts to rotate in a different direction as well. So as a result, for the wheel, going back to the wheel, that angular velocity that was originally pointing to the left, with the wheel then doing this, it starts to rotate itself so that it starts to point in a different direction. So in a sense, you start to rotate in the way that the wheel is trying, the wheel is going to fall counterclockwise, but as a result, the wheel turns into that fall to compensate. But, the idea behind that, it is trying to conserve its angular momentum. In this case, it's finding that its angular momentum is changing as a result of the torque. So the angular momentum, the spin is changing directions. So the wheel rotates into the fall. So you may have experienced this if you ride a bike, that if you are riding your bike and you lean to the left, you feel the bike turn to the left. And then you kind of stabilize and balance yourself back out again. It's essentially, again, that the angular momentum of your spinning wheels is adjusting to the torque. And so your angular momentum causes you to then turn in the direction that you're rotating, which allows you an opportunity to balance yourself back out. So there is truth behind just get moving, it's harder to fall down when you're moving. The fact is you have all that angular momentum that is helping you keep upright. And so you have to really torque the system in order to get your angular momentum to have you plop over on the ground. All right. I admittedly pushed forward without showing this demo. So here it is, not rotating. I let it go, it just falls over. Let it go, the torque causes it to fall over and fall on its side. Now if I do the same thing, but give it a little bit of spin, it clearly doesn't fall over right away. Actually, it falls over once it hits something. But it turns to the left instead of just falling to the left. And again, that's because there's some initial angular momentum that causes it to remain upright. How am I in time? Okay. This perhaps is the classic angular momentum problem. You have the ice skater. We've all seen this in videos. The ice skater is spinning and their arms are outstretched and they're spinning at some rate, but then they bring their arms together and they start to spin even faster and faster and faster. If you have a good computer chair, I should have recorded this. If you have a good computer chair whose ball bearings are smooth and you can rotate fairly quickly in your chair, you can do this. You can just sit in your chair, spin up the chair, so use your feet on the ground and get yourself spinning in place really fast. And then push off from the ground and keep your legs outstretched. And you'll be spinning at some rate. And then just pull your legs in without touching the ground, and you'll start to just immediately spin faster. So that's your try it at home homework. But let's see what's going on. So the idea is that you have the ice skater and they're spinning. So they have some angular velocity. They're spinning about kind of a line going through their body. And the idea is that when they bring their arms together, it appears like their angular velocity increases as a result. And let's try to see why. The ice skater is a great example because we can take the ground to be frictionless. I'll even draw it as ice. So we don't have to worry about any friction torques on the system. That also means that when I look at the system as the ice skater, there's gravity and there's the normal force, but those point along the axis of rotation. They don't exert a torque. Angular momentum is conserved for the ice skater. So the way to think of this is instead of the ice skater being a person, I'll think of it as a cylindrical rod with maybe a baton that has two, so you have the mass of the body, then you have maybe mass of hand, which I will treat as a cylinder and two balls. And the idea is that when they then bring their arms together, they have moved the hands that I'm representing just as point particles inside, closer to the rotation axis. And this is the axis of rotation. So since L is conserved, we can write just like what we did before. We can say that L initial equals L final. So if I figure out the total angular momentum of the initial system, I can set that equal to the final angular momentum of the finals, the angular momentum of the final system. So the idea is that if I want, this is an extended body. So I can write the initial angular momentum as the rotational inertia of the body, and then there are the mass of the hands times r squared, where maybe this distance here is r. This distance here is r. The length of the arm really is what that represents. Because you have most of the mass concentrated in a cylinder, for the inertia of the body, and then you have the rotational inertia of the hands, which are outstretched. And everything is rotating at the same rate. They're all, if that weren't the case, the ice skater would shear into pieces. And then when she brings her arms in, or they bring their arms in, they're essentially bringing the distance between their hands and the axis of rotation to 0 because they're bringing their hands into the rotation axis. So then this becomes just I body times omega final. So again, what did I do here? I wrote down the initial angular momentum of the entire system, which is the sum of the rotational inertias times the angular velocity of the entire ice skater. And then I set that equal to the final angular momentum, which is the rotational inertia of the entire system. But in this case, she's brought her hands into the rotation axis. So that no longer contributes anymore because the distance between the rotation axis and the hands are 0. Or, it's very small. I'm just going to approximate as 0. And then all of that is rotating at some new angular velocity, omega final. And so in this case, omega final equals omega body plus 2m hand r squared, all divided by the rotational inertia of the body, all multiplied by omega naught. I've given you no numbers, but just by looking at this, you know this is greater than 1. Because the denominator has the same thing, or rather the numerator has the same thing as the denominator plus something. So you know that, you could also write that parenthetical expression as 1 plus 2m hand r squared divided by I body. So it is 1 plus something. I don't know what that something is because I didn't give you any numbers. But I do know that this is greater than 1. Which therefore implies that omega final is greater than omega initial. Or she ends up spinning faster as a result. I don't know why I'm gendering her. They are spinning faster as a result. And again, what you're doing is you're taking your rotational inertia and you're shrinking your rotational inertia. You're concentrating more of the mass towards the center of the skater. As a result, if angular momentum is conserved, if the rotational inertia goes down, the angular velocity must go up to compensate so that their product is still the same. Else conservation is violated. Again, kind of similar to what we saw with a linear momentum. Consider a space station that has some central hub and maybe it has 4 kind of pathways to some outer ring where it's where everyone lives and all the habitants are. And it's spinning with some angular velocity initially. And it's out in the far reaches of space, far from everything. It then deploys, its arms, say, perhaps it's a telescoping kind of setup, where it can deploy so that it can expand to be a space station that has, some larger radius. So suppose this is a radius r, and it expands to have a radius of 2r. This might be some compact system where it's compact in order to launch it into space, and then through some sort of telescoping feature, it can expand itself out to a larger size. And the question is, if it was originally rotating with some angular velocity, what is the final angular velocity of this space station? Well, again, since my system is the space station itself, and there are no net external torques, because we're assuming it's far away from everything, the total angular momentum is conserved. Which means for a single extended object, I can write that I initial omega initial equals I final omega final. if all the changes are happening internally, then I can calculate the initial and final inertias and the initial and final angular velocities. In this case, perhaps there's some mass that makes up the space station. And it can't change, obviously. All the mass, mass is not being created as it expands. So whatever mass it has, after it's expanded was the same as what it had initially. And I could look up what is the rotational inertia for essentially a big hoop. You can think about that the spokes in the center part don't actually contribute anything to the inertia. So for a hoop, looking at the table, it's just mr squared times some initial angular velocity. And then it's still a hoop at the end, but now it's m2r being squared times the final angular velocity. Or mr squared omega naught equals 4 mr squared omega final. The m's, the r squareds go away. You get that the final angular velocity is 1/4 the original. This is essentially the ice skater in reverse. The ice skater moving their arms back out will slow down. That's essentially what's happening here. More of the mass is being moved farther away from the rotation axis, and therefore it takes more effort to get that thing to rotate at all. And as a result, the angular velocity decreases as a way to compensate while conserving angular momentum. I have two more. Consider a merry-go-round where you are it has some radius r, and you are standing at the outer edge of the merry-go-round, and you are spinning around the merry-go-round. I suppose there's some initial angular velocity that points straight up. The entire thing is kind of rotating in and out of the page by the right-hand rule. That gives you the direction it's rotating. The merry-go-round itself has some mass big M. You have some mass little m. You walk radially inward to the center of the merry-go-round. The question is, what is the final angular velocity of the U plus merry-go-round system? And again, just like with momentum, the idea is that you want to try to find a system where all the torques are internal to the system. So if I define the system as me plus merry-go-round, as I walk across the merry-go-round, I'm of course exerting a force on the merry-go-round. But by doing it radially inward, see how easy I can draw this. I need to zoom in. By drawing it radially inward, there's perhaps, I'm applying a force, friction is applying a force on my feet. That's what helps me propel myself forward. But if I stick with moving radially inward, I actually don't even exert any torques on the merry-go-round. The moment arm in the direction of the forces are parallel or anti-parallel. So there's no torque on the system. Even if there was, this is all happening internally anyway. But it turns out that there's no torque at all, which is convenient. I guess there's gravity pulling down on me and torquing myself down as I move inward. So there has to be some balancing force that maybe the support of the merry-go-round, I guess, is playing a role. But we'll assume that those are in balance. Else the entire merry-go-round would start to rotate, and tip over. So in this case, since again the rotation axis itself is not changing, I can write that the initial inertia times the initial angular velocity equals the final inertia times the final angular velocity of the system. Again, if the axis of rotation was moving around, that would be an issue. And it wouldn't be as simple as what I just wrote down. But if the axis of rotation is not changing and just stuff is happening internally, stuff is being re-shifted around inside, it's okay to just say the initial I omega equals the final I omega. So then really it just becomes a question of writing down what each of these represent. So I have the inertia of the merry-go-round itself, which is probably pretty well represented as a disk, plus my mass. So if I approximate myself as just a point particle, I start some blob of mass that is a distance capital R away from the rotation axis. So I contribute mr squared to the inertia. The final rotational inertia, after I've moved my way towards the center of the merry-go-round, I am now at the axis of rotation. That R has gone to 0. This just becomes I disk. It's just the inertia of the merry-go-round. Or you could think of it as there is my contribution, but it's multiplied by 0 squared. And so then similarly, you have I disk plus little m r squared times omega naught equals I disk omega final. As a result, omega final equals, again, this is very similar looking to what we saw with the ice skater. You have some fraction which is multiplied by, which is clearly greater than 1. So the merry-go-round spins up as a result. Again, you've concentrated more of the mass towards the center. It's easy to have that rotate compared to when it's spread far away from the rotation axis. I guess I had 3 more, but the last one's optional. So this is the last non-optional. An example of doing this with collisions. This is one from the book, but I forget which one. Suppose you have some sort of plank, which is fixed on a hinge or a screw that can rotate about that point. And it has some mass, let's say little m, and some length L. Actually, I'm going to move that up. It has some length L. And it's free to rotate if it wants, but it's not initially. Initially, there's no rotation. However, incoming is a bullet that hits and lodges itself right into the end of this kind of wood plank or rod or whatever it is attached to a screw. You can say bullet comes in and lodges itself in plank. I think intuitively we can think that if a bullet came in and hit it and lodged itself, the thing would start to spin as a result. Of course, now we can do a better job and say, how fast is it spinning? Or can I write down an expression that says how fast it's spinning? All right, so the bullet comes in, lodges itself. It will clearly start spinning. How much does it come in to spin? So here's an example. Like, it's kind of the analogy here is when we looked at linear momentum, we could look at the right before and right after the collision to determine and use momentum conservation before and after a collision. You can do the same thing here. I didn't really orient ourselves in terms of what direction gravity is pointing or whatnot, but it doesn't matter. I can look at immediately before and immediately after and look at what is the total angular momentum. So before, the rod is not moving. So the L of the rod is 0. But there is an L from the bullet, which is, in this case, R cross P of the bullet. And what is this R being measured from? It can be measured from whatever we want, but since we know it's going to start rotating about that particular axis of rotation, let's measure it from the axis of rotation in the center of the plank. Now in this case, I'm looking at immediately before the bullet lodges itself in. So there's a drawing that I made actually is not a very good one. And when I say immediately before, really I mean when the bullet is right here. And this is the axis of rotation. So this is the moment arm. And then there is some momentum that is also pointing straight up from the bullet. So in this case, if I think of the bullet as a point, this is essentially R is just the half the length of the rod, the length that goes from the center of the rod to the edge of the rod, times the momentum of the bullet, which is mv0. And then I can imagine that this rod is going to ultimately want to rotate counterclockwise as a result. So I keep this as a plus. And if you do the cross product, R cross P, L bullet of R cross P points indeed out of the page, which results in counterclockwise rotation, which we associate with positive. What happens after? Now it's a rod that is rotating with a piece of mass lodged into the end of it. So I would say L total is L rod plus L bullet, which is now lodged into the end. So again, you could look up in the table what it would be for a rod with a rotation axis right in the center. It's 1/12 m L squared, and then there's plus the big M, L over 2 squared, the rotational inertia of the bullet that is now lodged in the center. Or sorry, lodged in the edge. So bullet, rod. And then that all has some final angular velocity because it's all rotating together. And then you just set these equal to one another by angular momentum conservation. So then it just becomes mv0 over 2 L equals 1/12 little m L squared plus, looks like big M L squared over 4 omega final. So if I gave you M's and V's and L's, you plug all that in, you get a final angular velocity. And again, that's by applying conservation laws to immediately before and after the collision. You're essentially saying that the external torques, in this case, don't have enough time to do anything. Like what we said for linear momentum, where external forces, as long as it's immediately before and after a collision, don't have enough time to really do anything to affect the motion.